Okay, so I'm going to talk about balancing application portability and performance. So if you're looking at a software platform software, you're looking for various characteristics that it should have. So you want something that's robust and reliable, something that's commercially supported, well proven. If it's open source software, you want a good, strong open source community around it so that you know it's well supported. You want something that's proven. You don't want to be the first people to use it in an application. So you want something that's widely used, a de facto standard in the industry. You want software that's easy to use, that's high quality. So those group of things at the beginning, DPDK does all of those things very well. It's almost a de facto standard for data plane software. It's very high quality, it's easy to use, well documented. But then you think about other things that you want from platform software, and it's not as clear cut. So you want something that's very stable. You want it to be very easy to upgrade from one release to the next. So if you need to move from one DPDK release to the next, you want it to be as seamless a process as it can possibly be. And that's something, I'm going to talk a little bit about it later on, but that's something that DPDK is not good at the moment. We constantly change the API, so you have to make code changes every time you use a new release. So it's a difficult process to do that upgrade. And the last two things then, you want software which allows you to build an application that's very portable, but you also want software that allows you to build an application that's very high performance. And really, you can do, at the moment, one or other of those things. So there are various options you can select which give you great portability, but aren't as strong in terms of performance. There are other options where you get great performance, but not so good in terms of portability. And it's really that balance, what are the trade-offs between portability and performance that I want to talk about a little bit more. So if you look at it on the very simple diagram, so the vertical axis is how portable a solution is, and the horizontal axis is high performance. And obviously, up here we have kernel vSwitch, DPDK vSwitch. So they're very good in terms of portability. You can use the VirtIO interface to your application. That means it's nicely self-contained using a standard interface. You can live migrate it. It's a nice portable solution, but it's not the highest performance. The other extreme, we have our old friend SRIOV. So we all know the pros and cons of SRIOV. Fantastic performance, but you're very much tying your application to the hardware. Now, some of the limitations there are limitations of SRIOV. We're not going to change those. But we have been looking at, are there things in DPDK that we can do to make that easier? And of course, in an ideal world, you'd have something up here, which will give you the best of both. So easy to say that, but hard to do in practice. So the areas that we've been looking at are, if you take the vSwitch first, what can we do to try and improve the performance? So essentially to take that DPDK vSwitch bubble, keep the portability level of it, but move it to the right in terms of performance. So there's various optimizations that we can do on the vSwitch. That's leveraging NIC offloads. It's looking at various software optimizations. I'll talk a bit about those in a couple of slides. Second thing we've been looking at is, like I said, SRIOV has its limitations. We can't really change those. But a DPDK-based application using SRIOV, how can we make it easier to port that from one platform or one DPDK version to another? And then the other option we've been looking at, which seems quite promising and sits somewhere in the middle in terms of both performance and portability, is AFXDP. So it's at a fairly early stage. It's not as mature by any stretch of the imagination as VirtIO. It doesn't give you as high a performance as SRIOV, but it seems like a promising balance between the two. So again, I'll talk about that a little bit in a couple of slides' time. So that's the kind of context, the background. What I want to do is then talk about each of those three areas in a little bit more detail. So vSwitch first. There are various things that we've been looking at for vSwitch acceleration. And I guess when I'm talking about vSwitch, we focus mostly on Open vSwitch, OVS. So there are other vSwitches you can use, but the most commonly used one is OVS. So that's where most of our focus goes. So you can obviously do a full offload via SmartNICs. They have their pros and cons. You have to consider cost, you have to consider power, etc. Flexibility of the solution. I'm not going to talk about that anymore. There have been presentations at previous DPDK summits talking about SmartNICs. You can do partial offload on standard NICs. So that's things like offloading the lookup or using the TSO, TCP segmentation offload capability that's present in most of the popular NICs. So I'll talk a little bit about those. There's a couple of things we're doing in terms of software optimization. So the signature match cache went into OVS 2.10 as an experimental feature. I'll talk a little bit about that. Another thing we're looking at, I don't have a slide on it, is instruction set specific classification routines. So can we tune OVS based on the instruction set of the target platform that you're running on? So we would use things like SSE instructions if you're running on an Atom platform. We would use AVX, AVX2, AVX512, depending on the target platform that you're running on. So we have some infrastructure changes to make to OVS first to allow that. It's basically allowing you to plug in a highly tuned instruction set specific module via function pointers. But then the implementation of that we're looking at for the data plane classification initially, but it could be used in other parts of OVS. It could be used in the mini-flow extract. It could be used in exact match or signature match cache. And the last area then is looking at what we can do for VirtIO and vHost. And again, this has been covered, VirtIO 1.1 has been covered in other presentations at previous summits. I'm not going to talk about that, but the VirtIO standard is evolving. And with VirtIO 1.1, once we've finished optimizing that, we should get a significant performance boost from that. The other related thing that we're looking at is, can we use some kind of copy offload, like the Intel Quick Data, to offload the packet copy, particularly for large copies, and can we get some acceleration through that? So that's the kind of broad range. I want to talk about a couple of them in a little bit more detail. So first of all, the partial offload. So the diagram on the right is just your classic OVS pipeline, the extract, the exact match, the data path classifier, etc. And your typical fast path in OVS is through the EMC, the exact match. But it has a limited capacity, so it'll store 8K flows. If you miss that, then you're going to the data path classifier. It's slower. So what we've done now is we have added the ability to, via the DPDK RT Flow API, to offload matches from there back to the hardware. So then that gives you an even faster path where you're doing the classification in the hardware. So you're bypassing the lookup in OVS completely. So this is supported or will be supported in DPDK 1908 for the Intel Ethernet 700 series. That's the Fortville network adapters. It will be supported in a future release for the 800 series. That's the Columbiaville series. I don't know exactly what release that will be in yet. But if we look at what that gives us in performance terms, so the blue bars are without the partial offload and the green bars are with the partial offload. And it's for various numbers of flows and rules. So you can see, for example, if you're looking this column here, it's 10 million flows and 1K rules. And we get, I think it's a 220% performance boost by doing the partial offload. These two have 1 million and 10 million flows. The difference here is the number of rules. So these are 10K rules. So you've exceeded the capacity to offload flows in hardware, which is why the performance boost drops here. But if you compare the blue line and the green line, you still get a significant performance boost by using the classification capabilities of the hardware to partially offload Open vSwitch. Second thing we're looking at, and this is still work in progress, it's not upstreamed yet. I was hoping it would go into OBS 2.12. It doesn't look like it will. It looks like it might be 2.13, but it's work in progress anyway, is the TCP segmentation offload. So it's a capability that all the common NICs provide. So simple example, if you're going from a virtual machine through OVS DPDK out to the network. So without TSO, if you have a large packet, you have to segment that and do the checksum calculations in software. So you're burning CPU cores to do that segmentation and those checksum calculations. With TSO then, what it allows you to do is to keep that data intact. You set various flags to tell the hardware that you want to do the offload and the checksum calculation in hardware on egress. So what that gives you is you're basically moving that segmentation and the checksum calculations from CPU cores into the NIC. So you're offloading that processing from the CPU core. And I showed the egress case where you're going from a VM out to the network. If you're going from VM to VM, you actually get an even bigger boost because you never actually have to segment the data. So you simply go from the VM down to OVS DPDK and back up to the second VM. The data never gets segmented. You never have the cost of doing the checksum calculations or the segmentation. And performance boost we see for that. So what this is showing is the yellow-green bars are OVS without TSO. The dark blue is OVS DPDK with TSO, and the lighter blue is the OVS kernel. This is the intra-host, so this is going from VM to OVS DPDK to VM within the node. This is inter-host, so it's going from VM through OVS DPDK out to the network. So you can see, like I was saying, you get the biggest performance boost in the intra-host because you never have to do the segmentation, you never have to do the checksum calculations. So you get a fairly significant performance boost. Like I said, it's not done yet. We hope that it'll be in OBS 2.13 is what it's looking like right now. And the last OVS-related one then, the signature match cache. So this went into OVS 2.10 as an experimental feature. It's, if you like, an alternative to the exact match cache. You can use the two of them together. The key point of it is it stores only a 16-bit signature for a float. So it's very memory efficient. So with the same memory space where EMC can store 8K flows, with the signature match, you can do 1 million flows. So there's a very good paper from last year's OVS conference by Andrew Thurrer from Red Hat, where he did a very detailed performance analysis of the exact match cache versus the signature match cache. So it's worth looking at if you're interested in OVS performance. The really interesting thing, the blue line, I should start with the red line here, is the exact match cache performance. So it drops off as the number of flows increases, and then it essentially flatlines. The blue line is the signature match. What's really interesting is the point at which the signature match performance exceeds that of the exact match cache. It's basically a couple of hundred flows. So if you have a couple of hundred flows or less, then EMC is still more efficient. If you have more than a couple of hundred flows, then the signature match is a more efficient method. So there's various things that we need to look at. We need to look at, can we further optimize? Can we make the signature match the default and exact match optional? Is there optimization we can do in the exact match? But it's, like I said, Andrew's paper, I have the link there, is a really interesting reference if you're interested in the performance details. So that's vSwitch acceleration. So next thing is AFXDP, and there's a separate talk on this, which I think is later on. Yeah, okay. So I'm only going to touch on it at a high level, but very simple concept. There's basically three key parts. So you're using XDP, Express Data Path, in the kernel driver, and the ability to express filters through BPF. And then AFXDP is just a socket up to user space. So that user space application can be DPDK based. Jalong is going to talk specifically about the DPDK PMD for this, or it can be a a non-DPDK-based AFXDP application if you want. In terms of use cases, the areas that we're looking at specifically for this are containers and cloud native. So it fits very nicely into a cloud native type environment. It's a very good, efficient way to be able to share resources across multiple container-based applications in a very efficient way. The second case where it does very well is if you want to split traffic between the kernel network stack and user space. So you can see in this example, some of the traffic is going via AFXDP up to user space. Some of it is going via the network stack. So you can use hardware filters or you can use software filters via BPF to split that traffic at source. So instead of the model we have right now where all the traffic goes to user space and then you use something like KNI, DPDK's KNI, to inject back into the kernel network stack, you can split that traffic at source and send it to the right place immediately from the beginning. And the third area, and this is grayed out because it's not really a good fit for AFXDP, but just because it's a question that people ask, I wanted to put it in just for context, is how it works in a virtualized environment. So you can use AFXDP between the guest kernel and the user space application. The downside is that you still need a way to route traffic to the guest. So that still has to go via VirtIO or SRIOV. So if you're routing here to the guest via VirtIO or SRIOV, then the benefit of doing AFXDP in the guest is minimal. So it's grayed out because we don't really see that as a target use case at the moment. And in terms of performance then, so there are two sets of performance data. This one is an E5-2660, so that's the CPU generation known as Broadwell. If you look at L2 forward, so the dark blue bar is AFXDP. The lighter blue is the DPDK scalar PMD, and the yellow then is the DPDK vector PMD. So you can see for that simple use case, there isn't a huge difference between AFXDP and the DPDK scalar and vector PMDs. If you look at a later CPU generation, so this one is what's commonly referred to as Skylake. And if you look again at the L2 forward, you see a much bigger difference. So DPDK is much more highly optimized on the later CPU generations. AFXDP at the moment is not highly optimized on the later CPU generations. So that's work in progress to see, can we close that gap? Can we increase the performance of AFXDP there? And just future enhancements then. So again, Xiaolong's going to talk about the AFXDP PMD. I'm not going to bother covering that. But we're looking at further optimizations in the kernel. A key thing that we need to look at is support for offloads and accelerators. So AFXDP at the moment, one of the downsides to it is you can't use NIC offloads like DSO. It doesn't provide any support for any accelerators. There's a lot of work to do in the kernel community to agree the mechanism for introducing those to AFXDP. And the last thing that we're looking at is a BPF bypass. So at the moment, you have to have a BPF filter running here. But if you just want to pass all your traffic to user space, you don't need that. That's unnecessary overhead. So we're looking at, is there a way we can bypass that, make that more efficient? So the last area then I talked about was improving DPDK portability, usability for the SRIOV use case. So if you look at how that typically works, so DPDK is typically tightly coupled, statically linked to an application. So if you want to upgrade to support new hardware, a new NIC PMD, etc., you need to upgrade the application to a new version of DPDK. Upgrading to new versions is not easy. So we change the ABI in pretty much every release. So you have to make application changes every single time. So we've been looking at ways to move to a model where DPDK becomes your more traditional platform software. So it's dynamically linked, sourced from an OS distribution, has a stable API, and simplifies porting or upgrading of the application to move to new hardware. So if you look at the ABI stability of DPDK, this shows two examples. It's actually data that Ray Kinsler put together. I don't know, sitting in the back there. So if there are any difficult questions on this, Ray is the guy who knows all about it. But there's two examples. So GStreamer, it's an open source multimedia framework, much like DPDK, different application, different domain, but like DPDK in that it's a framework that you can use to build applications. And if you look at its API stability, it's pretty much 100% across the board, except one tiny little blip in one release a couple of years ago. You look at DPDK, and it's all over the place. And that shows you the degree of API changes that we're making. We had 2 releases where we were almost API stable, almost 98 point something percent. But we've never had one that's been 100% API stable. So Ray has been working with others in the community on a proposal to improve stability of the API in DPDK. It's a difficult problem because software developers contributing to DPDK want to be able to change whatever they want, whenever they want. Consumers of it want the stability, but the coders, the contributors, want to be able to make changes whenever they want. But basically, the proposal is that we'll declare a major API version every 2 years, and that API version will be supported for 2 years. And all new releases in that 2-year period will be backward compatible with that API version. So the API version would be reflected in the library's shared object name, and the API changes in that 2-year period would be handled. So addition of symbols, not generally an issue to add. Modification of symbols would be handled via API versioning. Removal of symbols would be handled in the next major API version. So we would guarantee for 2 years we're going to maintain a stable API. So just an example of that. So when the intent would be that when DPDK 1911, the LTS release at the end of this year, is released, we'll declare a major API version. We can pick a number for it, but call it V20 for now. And that will be supported for 2 years. So then all releases from 1911 to 2108 would be compatible with that major API version. So it should really simplify the process of upgrading. If you've upgraded your application to 1911 and you want to go to 2108, it should be, unless you want to take advantage of new capabilities that have been added, if you just want to upgrade, it should be a very simple process to do it because we'll guarantee backward compatibility of the API. And then in 2 years' time, when 2111 is released, we'll upgrade the API version, the major API version. So it gives a very structured, very logical, very well-maintained approach to managing the API, which we don't have at the moment. So there are a couple of other things that we've been looking at as possible changes in this area, but they're more thoughts at the moment. So one is consistency of DPDK APIs. So the concern is that ethdev in particular, the implementation of ethdev can vary between pull mode drivers. We've looked at what it would take to standardize that better. And it's a big effort to do it, and it's not clear that there's a return on that. So it's something we've been looking at, but not something that we plan to do right now. But we would be interested in any thoughts, input, feedback that people have. Have you seen problems with ethdev behaving inconsistently between one pull mode driver and another? The second area, and it's another area that we've been looking for feedback on, is software fallbacks. So there are lots of places where we have equivalent implementations in software. So you take something like the CryptoDev API, for example, you can accelerate in hardware, or you can accelerate using software libraries. The question that always comes up is, do we need to do more software fallbacks? So we don't have software fallbacks for RTE flow, for example. And do we need to make those more seamless, hide the details more from the application? There's pros and cons to doing that. And again, it's not clear that there's a need to do it because that complexity probably needs to be handled in the application anyway. And the last one is more up-to-date DPDK versions in OS distros. So typically the OS distros package the LTS releases, and they do that because those LTS releases are stable, they're well maintained, and that suits the needs of the OS distributions. But it means if you want to consume DPDK from an OS distro, you can't take advantage of the new features for some period of time after they're available. So the question we've been thinking about and talking to Red Hat and Canonical and others about is, do we need to do something to do more frequent updates of DPDK releases into the OS distributions? So again, if people have thoughts, input, feedback, that's another area we'd be interested in, and getting whatever input you have on those. And the last slide I want to put up, just because I showed some performance data, I have to show the standard legal disclaimers, so all the various terms and conditions that apply to performance data apply here. That's everything. Any questions?
Any questions? Yeah, team, you make everything clear, so no questions. Okay, thank you, team. Okay, thank you. Okay.